Okay, ladies and gentlemen, we are in section 8-2. This is recording number 1. Obviously, this is chapter 8. Now, what we're going to talk about now is the very first of our tests. Section 8.1 talked about the steps in the hypothesis testing, kind of a generic discussion. And now we're going to talk about an actual test that we're going to do at 8.2. 8-2 is the Z-test, 8.3 is the T-test, and so forth. So this is our first one in 8-2. I think it's worth the time to mention, just as an overview, that 8.2 is the Z-test for a mean, 8.3 is the T-test for a mean. So they're both testing the mean. They're comparing a mean of a sample to the mean of a population. What's the difference? The Z-test, you know standard deviation of the population, whereas in the T-test, you do not know the standard deviation of the population. And then the Z-test is for a proportion. We're going to compare proportions. And then chi-squared test is for the variance. If you have a variance that you're comparing, a sample variance compared to a population variance, is there a significant difference or not? That's the sort of thing that we're going to be looking at. And then I should have mentioned in this one, the test for a proportion, you're looking at a sample proportion, and you're comparing that to the proportion of the population. So all of these materials, all of these tests in chapter 8, is a sample compared to the population. Chapter 9 is going to be a sample compared to another sample. Okay, let me just say one more time the difference between chapter 8 and chapter 9. In chapter 8, we are comparing a sample to a population. So let me just use this as a standard sample that I'd like to use. Wheaties is a type of cereal. I'm not even sure they're still around, but Wheaties, Breakfast of Champions. For chapter 8, the canonical example that I will turn to is going to be, you take a bunch of kids out of a population. Let's say the population is elementary school kids. That's your population, all elementary school kids. And you take a sample of 100 kids and you feed them Wheaties. The population mean is 10 push-ups, and you take the kids out and you feed them Wheaties for a month or two, and then you have them do push-ups, and they do 15 push-ups. So 15 push-ups for the sample of eating Wheaties, 10 push-ups for the population. Now, you would be, if you were a talk show radio host on KFI, you'd say, well, obviously Wheaties has an effect, but that's not scientifically sound. And in order to decide if it's scientifically sound, you must do a statistical test. And in order to do a statistical test, obviously you need to know what statistics are, because it is entirely possible that those 100 kids that you picked out just by random chance are going to be able to do more push-ups than the kids in the population at large. So that's chapter 8 in a nutshell. So let's take a look at the material here. Okay, so let's take a look here. There's not a typo, but just a little bit of a confusion here. It says, in this chapter, 2 statistical tests will be explained. The Z-test is used when sigma is known. And I've already mentioned that to you, right? You use the Z-test if you know the population standard deviation. The T-test is used when sigma is unknown. Well, it's not just 2 statistical tests that are being explained. In this chapter, it'd be more appropriate to say, in this chapter, 2 statistical tests concerning the mean will be explained. We also are going to have statistical tests involving proportions, and we're going to have a statistical test involving standard deviation. So there's a little bit of a confusion there. Okay, so this section here, 8-2, is going to talk about the Z-test. So that's just one of those things you have to memorize. One of the few things you have to memorize is the Z-test is when you know sigma. If you don't know sigma, then you use the T-test, which is in section 8-3. Now this right here is worth its weight in gold here. This is what's really going on all the time. when we test for hypotheses, when we have a hypothesis test, we're going to use a statistical test, and it's based on this concept. The test value, now remember I said before, the critical value is the value of the boundary. So you find a boundary point and you say, if I'm on the other side of the boundary, I reject the null hypothesis. If I'm on the other side of the boundary, I don't reject the hypothesis. So is a boundary. You are on one side or the other of this critical value. The test value is not the critical value. The test value is what you get from your data, okay? And what you do is you have an observed value. Whatever, you take those 100 kids, you have them do their push-ups, you calculate what the mean is for those 100 kids, how many push-ups can they do, and then that's what the observed value is. So what's on top here? Observed value, observed value, take away the expected value. So the numerator here, the way I look at that is how surprised are you? Are you really, really surprised? Is the observed value quite different from the expected value? The expected value is, of course, what it is that you would expect to obtain if the null hypothesis were true. In other words, the hypothesized value. So remember, the null hypothesis is basically the status quo. That's what we expect to have true. We expect it to be this. The burden of proof is on the alternative hypothesis. So that's why the author says that the expected value is what you would expect to obtain if the null hypothesis happens to be true or not. I didn't say that right. The expected value is the parameter, for example, the parameter mean, that you would expect to obtain if the null hypothesis were true. So when we get this observed value, the mean of the 100 kids that ate the Wheaties, and we compare it to the expected value, that is on top what I look at and I say, how surprised are you by the results? And then what's on the bottom here? The standard error. If you look back on page 346, that was the discussion about the central limit theorem. On page 346, the standard error was defined in a certain way. Let's take a look at it. Okay, so this is on page 346. This is the so-called standard error of the mean. So that's the standard error of the mean is the standard deviation of the sample means. In other words, you look at all of these x bars. All of these x bars are considered as random variables. You look at them and they have a distribution. They have a distribution that looks like a normal distribution. The mean of or the mu of the normal distribution that the x bars consist of numerically is equal to the mu of the population. So that's what he says right here, that all these x bars, they will approach a normal distribution, and then this distribution of the means, it will have a mean of mu, that's numerically the same number as the population distribution, and it will have a standard deviation of sigma over the square root of n. So, it's just the way it is, okay? Beyond the scope of this class to prove that. So that's called the standard error of the mean. Well, this is important because in this hypothesis testing, when we're doing the z-test, we are basically using the central limit theorem to do the test. So that's why he brings this up right here. Okay, so on the top here, on this test value, this is how surprised are you, and underneath is what's referred to as this standard error. Let me give you a very mundane metaphor for this, okay? If I were to say to you, how wide is this room? And if all you did was give me a number, if you said the room is 40, that would not tell me anything. You have to tell me what kind of a yardstick you're using. You have to say it's 40 feet, it's 40 yards, it's 40 meters, whatever it happens to be. So merely giving me a number doesn't tell me what I need to know. So the yardstick that you're using it might be meters. Well, the same thing applies here. This standard error is the yardstick that you're using to decide how surprised are you. Like, for example, if an observed value take away the expected value, if it was the answer was 2, that 2 divided by the standard error tells you how many standard errors are you surprised. How surprised are you? Okay, so we'll see in an example how this works. But here's my recommendation, and I strongly urge you to do this. Write this down. Every single problem you do in chapter 8 and chapter 9, make sure you remember that the test value is on top is, you can write this down, observed value, take away expected value over the standard error, but then write down equals, and then your common sense language is on top you have, in the numerator you have, how surprised are you, and in the bottom you have yardstick. That will help you really get the gist of this in a common sense way. Okay, so the z-test, here's the formal definition. Obviously, it's a statistical test. It's a test for the mean of a population, and there are some limitations. If the population that you come from, all the 6th grade kids that you're drawing the population from, or I'm sorry, you're drawing the sample from the population of all the 6th grade kids in the universe. Okay, so the population is all the kids in the universe. That's the population. If that population is normally distributed, then we don't really care what the size of the sample is. On the other hand, if the population is not normally distributed, then we have a requirement that our n, the sample size, has to be 30 or more. So that's just a very easy requirement to meet, right? I mean, if it's not normally distributed, well, go take some more samples, right? Or take more people in your sample group. Okay, so if you know sigma, it's the z-test. We'll see here in the next chapter, the next section rather, if you don't know sigma, then you use the t-test. So I'll let you read that for yourself. It's very clear, I think. You got the x bar, that's what you observe, that's your observed value. Your expected value is mu, because for the null hypothesis, you are assuming that it's mu, all right? This is the yardstick down here. This is what is commonly referred to as the standard error, which I thought he said that somewhere. Yeah, here it is, standard error. Okay, all right. So here he's kind of explaining where this comes from. And what he's basically saying is that it's the central limit theorem. The central limit theorem says that you can use the standard normal distribution to approximate the distribution of the sample means. So all of these x bars, out of all of the bazillions of possible ways that you could take 100 kids out of the population, those x bars can be considered a random variable. And when you take your sample of these kids, the kids that you picked, that x bar, that has a certain distribution, and you compare that up here, that x bar that you pick, those 100 kids, take away the mu, the mean of the population. That's how surprised are you. These kids that you picked, how different are they from the mu? Okay, and then the central limit theorem justifies this procedure, because what the central limit theorem says is that you can use the so-called standard normal distribution to approximate the distribution of sample means. Okay, so here's the requirements. Okay, let you read that yourself in your book. Okay, all right. So here's the steps. As always, you state the hypothesis, you find the critical values, you compute the test value, make the decision, reject or don't reject the null hypothesis, and then you have to summarize the results. This is a true statement. It is so confusing, so confusing. So let's do an example in the next video. Example 8-3.